G'day everyone and welcome to the Trekzone Spotlight. Well, we're still here at the University of Queensland on location once again because Professor Tamara Davis is going to join me again to discuss black holes and dark matter. So it's all about black holes and dark matter. Professor Tamara Davis, thanks for joining me again.
Great to be here.
Let's get into it.
Yep.
Black holes.
Yep.
What are they?
Okay, so black holes are actually not that mysterious. If you took all the mass from the Earth or the Sun and compressed it into a really small area, you would have a black hole. They're just super, super dense things that are so dense that light can't escape. So if I try and jump off the Earth, I can get a certain height, but really not that far. But light has no difficulty escaping. It's traveling very fast, but light can't escape from a black hole. That's why they're called black. And
are they actually black?
Well, in detail, probably not, because that's one of the things that Stephen Hawking was famous for. He discovered that black holes should actually glow extremely faintly, not in something that we're actually going to see with our eyes, but they'll actually give off a little bit of light, and that's called Hawking radiation.
And have we found that yet? Or is it still hypothetical?
Yeah, the Hawking radiation would be way too faint for us to detect, but we have seen black holes. And by seen, we've seen them in a couple of ways. Firstly, we've seen stars orbiting something that's not there. So the center of our galaxy is the prime example of that. You've seen stars orbiting something that is millions of times the mass of our sun. We can weigh it because we know how tightly things are orbiting it. But we can't see it. And so that's the strongest evidence that we have for a supermassive black hole at the center of our own galaxy. But we've also seen these supermassive black holes at the centers of other galaxies, and we see those if they're hanging out there at millions or even billions of times the mass of our sun. It sucks a lot of material in, and galaxies are typically full of gas. So as that gas falls in, that gas gets really hot, and it emits in X-rays all the way down through optical and stuff as a really, really hot glowing thing. And when that happens, we say it's an active galaxy, and we've also detected it that way.
Does that mean that a galaxy is going to collapse in on itself?
No, because it's just like the same as the solar system doesn't collapse in on the sun. All they are, like if you took the sun and compressed it into something the size of the Earth, it would be a black hole. And here on Earth, we would just happily orbit the black hole. Not a hell of a lot would be different, except it would get a lot colder. Because there's no sun shining down on us anymore. But in terms of gravity, they're not that sort of vacuum cleaner-ish that they'll immediately suck everything in.
Something else that you're looking for is dark matter.
Yes.
What is dark matter?
We don't know.
Is that why it's dark?
I would love to be able to answer. But dark matter and dark energy are two really, really interesting things. So dark matter has been known about since the 1930s. Basically, as soon as we looked up and looked at the motion of galaxies, we saw that galaxies were moving too fast. And by too fast, I mean they were moving too fast to hold themselves together. Initially, it was galaxies orbiting other galaxies in clusters, and then people looked at individual galaxies and that spiral galaxy and how fast that spiral is moving. And if I take a string with a weight on it and like spin it around my head, I know how hard I have to pull to make it spin at a certain speed. And the faster I want to do it, the harder it is I have to pull. So when you look at galaxies spinning, they're spinning too fast to hold themselves together. There's not enough mass in the galaxy that we can see in stars and gas and other things that might shine to hold themselves together. That was the first really strong evidence that there was some dark matter out there that we couldn't see. Now, initially we didn't know whether that was maybe just our laws of gravity are wrong, or maybe there's a real substance out there that's something that's not on the periodic table. It turns out that it's almost certainly some other kind of particle out there, because we've now detected it in many, many other ways as well. Things like looking at the very, very early universe, the cosmic microwave backgrounds, this afterglow from the Big Bang. We can see traces of dark matter in the patterns that we see there. And I could go into that, but that might take a long time. We can see light bending around clusters of galaxies and measure how much mass is there by the amount that light bends. That's called gravitational lensing. Dark matter's there again, in a variety of different ways, all confirming that there's something out there. We just don't quite know what it is yet.
And it's all about understanding the universe that's around us to know how we fit into this big scheme of things, really, isn't it?
Yeah, so the thing that I'm most interested in is the fundamental laws of the universe. The reason we look to space to understand these is that there are experiments going on up in space on time scales, on length scales and energy scales that we just can't possibly replicate with anything that we try and do here on Earth. The big question is, how do quantum physics and gravity work together? This is the big mystery at the moment that we're trying to solve. And dark matter and its friend dark energy, which I haven't talked about yet, are two of the big pieces of the puzzle that we need to understand if we're going to understand how general relativity, our theory of gravity, works in conjunction with quantum physics, our theory of particles.
How does dark energy fit into that?
Okay, so when you're looking at the energy density of the universe, 5% of it merely is made up of stuff that fits on the periodic table or is light. 25% is dark matter, 70% is dark energy. And as far as we can tell, dark energy is distributed smoothly around the universe, and it's causing the expansion of the universe to accelerate. So dark matter clumps and holds galaxies together. Dark energy is smoothly distributed and pushes galaxies apart. And the difference is dark matter holds individual galaxies together in clusters, whereas dark energy is pushing distant galaxies away from each other. Now, it means that we've discovered something which is causing gravity to work in reverse. Gravity is pushing instead of pulling. Now until that was discovered in 98, 99, we had never seen that happening. We had no reason to expect that gravity should ever push. So trying to explain that might be the key to understanding quantum physics and gravity, because there's some quantum physical effects that might cause gravity to work in reverse, and we're trying to figure that out.
I'm running this through my brain at the moment, and it's absolutely fascinating, and it's absolutely amazing to hear that all of this stuff is going on, and it's all happening, or Australia is part of this global community to find all this out.
Definitely. They're building a dark matter detector down in Victoria. We're part of these big international surveys to try and understand dark energy, and we're also have lots of experiments here in Australia with big telescopes that we're trying to measure the dark matter and dark energy more precisely, because by measuring their properties we'll learn a little bit about what they might be.
Well, how do we measure dark energy?
Okay, so the main way that dark energy has been measured is with supernovae, exploding stars. So ever since the 1929, when Hubble discovered that the universe is expanding, people have wanted to know whether that expansion is going to continue forever, or whether gravity would slow it down enough, the gravitational pull of all the galaxies on each other, to stop that expansion and recollapse. So the question was like, if I jump up in the air, I'm going to come back down to Earth because I can't jump very high. But if I was powerful enough to jump and propel myself at 11 kilometers per second off the Earth, I would have the escape velocity, and Earth's gravity wouldn't be able to pull me back down. So the question was, do the galaxies, as they expand and they move away from each other, have the escape velocity or not? It wasn't until the 1990s that people were able to answer that question, and supernovae were the key. Because these particular type of supernova always explode to the same brightness. And that means just by looking at how bright they appear, you can tell how far they are away. So you can use them to measure distance. And that's really important, because we have that one aspect, distance. And the second thing that we measure is their velocity. We look at the spectrum of light, and when something's moving away, the spectrum gets stretched and and blue things appear red. Doppler shift is one way to describe it, or it's redshift, is what we call it. So by measuring the redshift, we can measure how fast things are moving away, and by looking at how bright the supernovae we know how distant they are. Now, these supernovae are so distant that the light has been traveling for multiple billions of years sometimes. So we're really looking at the universe as it was billions of years in the past. So you can compare how fast it was receding there by looking how fast supernovae were going away to how fast it's expanding now. And the surprising discovery that they made in the 1990s was that expansion is now speeding up. So that's as though I gently jumped into the air and was accelerated off into space. Gravity is working in reverse for some reason. We don't know why that's happening. We don't know what's causing it, but we give a name to that cause and we call it dark energy.
The future, dare I say, looks dark or black, possibly. Professor, thanks so much for your time.
Thanks so much for having me.